In this video, I'm going to talk about adversarial defenses. In the last video, I talked about how it's actually quite easy to generate adversarial examples of inputs or sort of perturbations on inputs that fool the neural network into classifying it incorrectly. So in this video, adversarial defenses, what can we do to avoid that from happening? So the goal is to see how we can train our neural networks so that they are not so easily fooled. It's still an open question, but there are some things we can do. The first method maybe has already occurred to you, adversarial training. So this is where we can add adversarial samples that were generated back into our training set and train those to be correctly classified. So in the graphic here, you can see we've got our data set and we've got our trained model here. Let me zoom in a bit. Trained model, which I'll call F here. And from F, we're going to generate a bunch of adversarial samples. Then we're going to add that to our data set and then retrain on that and get a new model F. And then we can repeat this process. And over time, it becomes more and more robust to those adversarial samples. Now, this works somewhat, but like many adversarial defense mechanisms, it doesn't really solve the problem in a sort of fundamental way. There's another method which I haven't gotten written down here, but it's called gradient masking. Now, you can imagine that when you're training a neural network, you're basically looking for some minimum in your loss function. You're in parameter space and you find some minimum. So the adversarial attack is looking at that loss function and climbing back up, right? Climbing out. So you can do some things like maybe you can fool it. Let's say around your minimum, you have like a little, there's your minimum, but outside of your minimum, there's almost like a little hill, or maybe one direction goes steeper than the other direction. Maybe going this direction is going to sort of take you up to some new heights, but going this direction just goes up a little bit and then there's like a little local maximum. So if the adversarial attack starts going up in this direction, reaches some local maximum here, it's going to get stuck. So that's called gradient masking, where you distract or basically push the gradient ascent method to some nearby local maximum where it's kind of harmless. I'm not going to focus on that method though. Instead, we're going to talk about this different idea. What if we incorporate a miniature adversarial attack into every gradient step while training? So let me introduce you to TRADES. Now this is one of those acronyms that's really stretching it. TRADES stands for Trade-off Inspired Adversarial Defense via Surrogate Loss Minimization. So if you Google that title, you'll find the paper. It's by Hongyang Zhang, who I mentioned last lecture, and I'll mention him again in this lecture. Now this method, if you read that paper, there's quite a lot of theory in it, and I'll allude to it, but I won't go into it. And as I sort of jokingly say in my notes later on, I don't go into it because I don't understand it. That's a good reason. Okay, so let me at least outline the part of it that I understand. So consider a neural network model F, which maps from some input space X to real numbers. And we have a data set, capital X, capital T, of X is taken from the input space. T are targets. Now it's a classification problem, so we're going to have plus ones and minus ones. Those are two classes, as opposed to 0 and 1, and you'll see why right away. So in that case, then the sign of f of x is the class of x. So the classification is correct then if f of x times the target is greater than 0. So if the target is plus 1 and my model f of x returns something that's positive, then that product's going to be positive. If, on the other hand, if my target's positive 1 and my model outputs something negative, when I multiply those two together, I'm going to get a negative number. Okay, or if my target's -1 and my model outputs a negative something, multiplied together, you get a positive again. So again, that's a correct classification. So it's this plus minus 0 is the threshold between the two classes. Okay, in this case, the classification loss can be written. Now I'm calling this, well, not me, this is called the natural loss. Because it's basically, it's not part of, there's no adversarial stuff going on here. This is basically saying just how many of our samples do we misclassify. It's the expected value over our data set D. Did I call it D up there? I didn't, but let me just say D is that data set. It's the expected value over our data set D of, now again, this is this indicator function. It returns how many times the event in the curly brackets is true. How many times f of x times the target is less than or equal to 0. So that's a misclassification. And this natural loss is going to count how many times that happens. So if our data set, let me just sort of make sure it's clear what I mean by natural loss. We've got data set here, and one class, and the other class is here. As we've seen, they often overlap each other, even if we do know the actual model would be something like that. That would be the decision boundary. You can see that there are very legitimate elements of each class on the wrong side of the decision boundary, just because there's some noise added to it. Okay, that's a natural loss. Now, if we want to consider how our model will perform under adversarial attack, we need to be a little more pessimistic, right? Because there's going to be some wiggle room trying to make our lives difficult. So we consider the robust loss. Okay, now this is the expected value over our data set of, now we're going to count the number of times that, now it's not just about the training, or sorry, the elements, the training or test, no, the training elements themselves, I guess it's test actually. It's about their neighborhoods, and are there adversarial examples in their neighborhood. So the number of times that there exists an x primed in the epsilon ball of x, such that that x primed gets misclassified. Whoops, that's x primed times the target. Yeah, less than or equal to 0. So what we're looking for is the wrong class of this adversary. Okay, so this robust loss has this built-in pessimism that looks for the worst case scenario in the neighborhood of x. I was going to draw this. There's a decision boundary here, and this is the wrong side. So we'll have some x's over here, and these are correctly classified. But we'll have some x's over here that are incorrectly classified. And then we'll have some x's out here that are correctly classified, but there is an x, oh, yeah, the old erase thing. There is an x primed in the epsilon neighborhood that gets misclassified. So our robust counts both of those. Really quick joke. A lot of people don't understand my sense of humor. See what I did there? Okay, speaking of sense of humor, for theoretical reasons, I won't go into the theory behind this method. And what that means is I don't understand, as I mentioned before. It has to do with these surrogate functions and the conjugate of the surrogate functions, and this classification calibrated functions and conditional phi risk, and these things that I'm not really, haven't really studied. But luckily, this method can still be understood intuitively without understanding the theorems. The theorems basically, they use these methods that I just mentioned, these kind of mathy buzzwords, to come up with lower and upper bounds for the robust loss. And turns out they're tight bounds. And from those bounds, they derive this other formula for the loss. So anyway, but we're going to use a surrogate loss function, phi, and instead of using our binary classifier. So before, we basically had this thing that counts the number of wrongs. So basically counts when alpha is less than 0. So when the input's alpha, it'll basically return a 1 when alpha is negative, and then a 0 if alpha is positive. So it's counting the times that the input is negative. We're going to use a smoother version of that. This phi of alpha. Now there are a number of different versions. What I've drawn here looks like a logistic function, and logistic function does in fact fit the bill for this kind of thing, and you'll see in your assignment that you'll be playing with a logistic function. Okay, if we're going to use this phi, which is a surrogate for counting the number of incorrect classifications, I guess it's smoother. Maybe that's part of what motivates the theory, why this has theoretical guarantees behind it. So reposing our optimization task using this phi instead of the indicator function, we're looking to minimize over models F the expected value over our data set of phi of f of x times t. So if f of x and t have the same sign, that product inside phi is going to give us a positive number, and we're going to be over here giving a low phi value. If f and t have negative signs, that product is going to be negative, and we're going to be sampling phi over here, which is much higher, so it'll be a higher loss. So you can see how it's a smooth version of the same idea. Now, what I just showed there is the learning algorithm, just training it to be a classifier. Let's build in the robust part of it. We can try to train a robust model using the combined loss, minimizing over the models F, the expected value over the data set D of, so this is our natural loss, f of x t, plus, now this is the pessimism part. This is kind of like, okay, what's the worst that can happen? So the worst that can happen is we can get some maximum value of our loss of our phi function. So we're going to look in the epsilon neighborhood of x, like we talked about before. Look for the neighborhood element that gives us the worst outcome. Okay, so putting these two together, this first term, which I'll call 1, tries to ensure that each x is correctly classified. Now term 2, that part there, it adds a penalty for models of f that put x within epsilon of the decision boundary. So we're in the business here of changing our model f, right? We're minimizing this loss by adjusting our model f. So we have choices for f. This term is going to penalize f's that allow nearby adversarial examples. So what we do is we find a nearby sample that gives us the worst case scenario, and the minimization, the outer minimization here says try to avoid that. Try to find an f that avoids that. One is really the trying to ensure that the classification of the data set's correct. The other one is basically saying the worst case scenario, let's try to avoid putting the decision boundaries close to our samples. If we can put the decision boundaries, place them away from our samples, then an adversarial attack that's within an epsilon ball is not going to be able to reach the decision boundary. So here's the implementation. Normally when we're training a neural network, it's gradient descent, right? You have your loss, like term 1 here. Forget about term 2. We'd have term 1, we'd evaluate it, get the loss, and then compute the gradients of the loss and take a step down the gradient. Now for each of those gradient steps, we're going to add some stuff. For each gradient step, we're going to add this sort of pessimistic process of looking in the neighborhood for an adversarial example. So for each gradient step, we're going to run several steps of gradient ascent to find x primed, right? Because this is maximizing the loss. So we're going to take a few steps in an effort to maximize that error and find an x primed that gives us a larger loss. Once we find that x prime, we fix that x prime. You can see there's this maximization process inside a minimization process. So you can think of it this way. We're minimizing over f. Oops, I erased again. Yep. We're minimizing over f. Great. So once we're inside those brackets, though, we're thinking, okay, we have a particular f now. We evaluate our loss. For a particular f, we can look at this loss term, this term of the loss. So for fixed f, we try to find the worst case scenario x primed, or the adversarial example. Once we find it, we fix x primed, and then we go back out and say, okay, now we have our loss function. It's got these two terms, term 1 and term 2. The max is no longer there because we fixed our adversarial example. Now we look at those two terms and we say, how do we adjust f to minimize this loss? How do we take a gradient step to reduce this loss? Okay, so we run several steps of the gradient descent to find x primed, then we fix it. Then fix x primed, and then we evaluate the joint loss. So the loss is phi of f of x, t, right? That's the classification, plus some regularization parameter times this adversarial part, f of x times f of adversarial x. So this is a regularization parameter. Now we use the gradient of that loss for our gradient step, for our connection weights and biases, that adjusting our model f. So this is more expensive because for every gradient step, we now have this sort of inner loop that does a few gradient ascent steps to find an adversarial example. So let's look at results. On the left here, I'm showing this sort of original, or let's call it naive training method. And each dot here is a training sample, and you can see that there are there's the yellow class and the blue class. And after it's been trained, you can see all the elements are classified properly. All the points are properly classified. But it's also drawn on the decision boundary. And you can see that there are many places, and around each point, it's drawn on the, it's drawn on the epsilon ball, which in this case is the using the infinity norm. So if you look at a number of these epsilon neighborhoods, you can see a lot of adversarial examples. So for example, this one here, you can see in this little corner here, there's an adversarial example. There are adversaries here. Up here, this that's a corner of the epsilon neighborhood of that point that has elements that will be misclassified. There's some here. Where else? Here, here. So lots of places where in the epsilon neighborhood, basically the decision boundary is within the epsilon neighborhood of the even correctly classified points. Now, if we train using trades, remember, it's got this extra stuff built into it saying for each gradient step, look for cases and penalize for cases where we can find an adversarial example nearby another sample. You can imagine if built into this maximization process here, if you, oh yeah, it's within the epsilon ball, right? Okay, so you look for the worst case scenario in the epsilon ball, and so by the end of that, and as you can see here, the decision boundary is outside all of those epsilon balls. You won't find, I don't think there's a single case here, it's not always quite this clean, but you won't find it, or you tend not to find cases where the decision boundary cuts through one of the epsilon neighborhoods. So if you were to try to run an adversarial method on this model on the right, and you constrained yourself to only epsilon neighborhoods of your samples, you would not be able to fool it at all. You wouldn't be able to find an example that actually changes the classification. So the trades method won the NeurIPS, Neural Information Processing Systems, 2018 Adversarial Vision Challenge. And NeurIPS is pretty much the premier conference on neural networks. So this won that year, and since then it's just basically become one of the standard top of the line, what am I looking for? State of the art methods. As of March 2021, in Robust Bench, which is this web page I've got linked here, 5 of the top 5 and 9 of the top 10 methods on that leaderboard are all based on the trades method. So the idea is basically in the region, in the neighborhood of your points, you want to flatten out your flatten out your model so that you don't get, so that it doesn't cross the decision boundary in the epsilon neighborhoods of your samples. So I'd like to acknowledge again Hongyang Zhang, and there's a link to his webpage here for inventing the trades method and giving me some code and some of these graphics.